You can hear me. Can anyone just go on to, I'll have a look if it's working. Okay, I think now everything's working the way it should, including sound. Okay, I think thank you, Philip. I think now everything's working the way it should. And I'll switch off the sound here, otherwise I'm gonna hear myself talking. Okay, sorry about last time. Sorry about the sorry about last time where we recorded completely without sound, which was not particularly helpful to anyone, especially also not my students here. So, okay, what are we going to do today? Today, we're going to go through how to actually do analysis on data, how to model a grain boundary. Maybe we'll get to model a phase boundary as well. And then from the grain boundary, calculate interfacial axis and calculate a proxygram. And I'll also go through the programs and show you how to do that. And what the code in the programs actually means, so that you can, if you have your own ideas what you want to do, you can do that pretty easily. It might sound a little bit lengthy, the whole process, when we're going through it right now. But just to give you an example, this is a grain boundary I just analyzed this morning. This is actually a very typical case. So phosphorus at a grain boundary in steel. And the entire analysis from getting the data to creating the model to creating useful, to finishing the analysis took me about an hour. So it doesn't actually take too long if you get the hang of it. Um, anyway, of course, this is someone's data that I can't just give out, so we're going to use some reference data. And for that purpose, as always, you can go onto GitHub. So if you go onto GitHub and you type in Atom Probe tutorials, you'll find all the code that we've used last time and this week. So I've started actually calling them by week. So what week we introduced them. So now we've got week 7, and of course it's week 7 in 2016. So I also added that. And you've got all the algorithms that you need, and all of them are tested and work. Apart from this one here, centroidal Voronoi tessellation. That one doesn't work on my computer because it turns out that that my university has not purchased one of the toolboxes that I've used in there, which I used to have access to while I was in Sydney. Anyway, it's just a minor one. It's just a an intersection of a polygon with a line, so I'm pretty sure I'm going to be able to code that myself without having to pay, without having to get the university to buy the entire toolbox. But yeah, it shouldn't be too hard. If you join in regularly, or generally if you work with code, one very nice thing to have is to get yourself a GitHub desktop, which means you can clone the repository from GitHub onto your computer, and also manage all the data with it. So you will get any updates pushed and so on. And just the way I push them on, you can just download it, and you don't need to download the whole file or the whole folder every single time, and deal with things um, being added. Anyway, so since I can't give you any data for today's tutorial, the first thing we're going to do is create our own data. So we're going to create reference data, and for that purpose, there is an algorithm here called Synthesize reference data. And all you need to do is just type that in. It's not a function, it's just a script. Um, and once you let that run, it creates 3 POS files, each of which is 100 and one's actually 200 megabytes in size, which are a grain boundary, a phase boundary, and a precipitate. They're of course not real grain boundaries, phase boundaries, or precipitates. They're just um, well, um, they're just synthetic versions of it, and you'll see that in the master charge windows and everything. But the good thing is you can distribute it with very little bandwidth, with very little um, internet bandwidth, and it doesn't belong to anyone. So no, I'm not going to get into trouble with anyone. Anyway, I'll just take those 3 data sets so that they won't always get pushed along with the other things onto GitHub. Because, downloading that from GitHub would be half a gigabyte downloading. So I'll just go one up, new folder, example data, and I'll get those 3 over. You can just leave them in there. It's just because I might need to push some other algorithms while we're working, and then I don't want it to upload half a gigabyte of data. Yeah. All of the reference distributions that created that are in the variables here, which we're not going to need, so we're just going to clear out all those variables. But if you want to look into it, there's going to be a precipitation concentration, precipitation radius, all those things that are used in there, and the concentrations that created it. So I could, for example, go and have a look at the phase boundary concentration, how it develops and how it was synthesized, but you're going to see it in a minute anyway. So I'll just clear out my variables by typing in clear, and we'll start with a clean slate. And I'll also restart Blender just so that we start with fresh data here as well. So with Blender, to move along with the tutorial today, what you have to have installed already is the Blender plugin for atom probe data, which you can get from my webpage. I think everyone here has done that already, right? We've done that last time. Great. So we'll just go and delete everything that was in there by just pressing A and then pressing A again. So select, deselect. If everything's orange, that's what it should be. And then just go press X to delete. And select the POS file. And there must be Dropbox, research element. Okay, where's my atom probe tutorials? AP tutorials, there we go. Example data. And we'll start with the test grain boundary.pos. Select the POS file. And for the range file, there's actually one in the uploads. So if you go in the atom probe tutorials, there's tutorials.rng. And we'll have a look into what an RNG file looks like in a second. So select range file, and then you go load POS range. It's all here, and then you go bake to object, which for a 200 megabyte dataset shouldn't take too long. So 200 megabytes, it's about 12 million atoms, or a 20 by 40 by 40 by 80 nanometers. I made it with 50 atoms per cubic nanometer, which is about the density of a real material. But of course, because of the detection efficiency of the atom probe, it would be a little lower. The density in your atom probe dataset. And that's the dataset, so it's nice and cubic. BL stands for bulk, SL stands for solid. So if we switch off the view on the bulk, you can see we've got the solid here, and if you look from the side, we can see that there is a faintly visible higher density in the middle than there is on the side. And the reason why I only made it a little bit higher concentration in the middle is because I want us to run into a variety of different challenges so that it doesn't come unprepared when you're working on real data. The one that I showed just before had very clear segregation, which is actually very, very common, but easy is boring, so we're going to do it a little bit more challenging. Anyway, so this is our reference data for the grain boundary. And if you look at the grain boundary from the side, it's a little bit hard to see. Sorry. You can see that there is a higher density region here and a lower density grain boundary region. So in other words, I've made the grain boundary to have a higher excess on one side than on the other side. And the reason for that is that next time we're going to go into local analysis of interfaces. So today we're going to do global analysis, which means we're looking into for the entire grain boundary, what is the interfacial axis and what is the concentration profile across it. So we're going to do a proximity histogram across it. In this case, of course, a cylinder would do it as well because it's flat, but then again, usually grain boundaries are for a variety of reasons in atom probe data not flat. Sometimes they're also in reality not flat. Anyway, but yeah, for now, we're actually just going to do single value things, and next time we're going to get a little bit more challenging, and we're going to do mapping and local proxygrams. So what that means is that with the mapping, you can map how much interfacial axis you have in what area, and with the local proxygrams, you can, for example, make a proxygram here and one here. Or the other thing you can do is, and I mean, on a grain boundary, something like that would very rarely happen because diffusion is very fast across here. So unless you've artificially made that, it's probably not going to happen. But what can happen very easily is that you have a precipitate which has a cube shape, for example, a superalloy, and you want to have a look at the segregation at the corners and the segregation at the edges versus the flat parts. And there's actually, I can tell you, we have seen it in data that there is significant differences. Anyway, so that's it that's the data we're going to be working with for today. So let's load that into MATLAB by simply typing in. Once you're in the folders, you need to be in the Atom Probe tutorials folder that has all the stuff in it. In your case, it will also have the data in it. And then you just type read pos. Oh, sorry. Pos equals read pos. Sorry, I also did some cropping. And this saves everything to a variable called pos. So what I'm trying to do is always use the same variable names, which means I can use the MATLAB's autocomplete all the time and then just shuffle data around however I need it, and you'll see in a second what that actually means when we're starting to pull out solutes. But anyway, just go pos read pos. In my case, I need to go one up and into the example data and load the test grain boundary. So we've got the pos variable out now. If you look at it, it's roughly 13 million atoms, which is not too big, but sort of a typical dataset size. And if you look into the variable, you can see there is the coordinates of the individual atoms, synthesized atoms, and in the fourth column, where the master charge would be, there is a 1. And there's a lot of 1s, and occasionally there's a 2. And I've just made it in the synthesized data. 1 stands for solute, 1 stands for bulk, and 2 stands for solute. That's all there is to it. So we'll say that our solute equals pos fourth column equals 2. And now we've pulled out all the solute, which is about 150,000 atoms. And we're going to need that to fit the grain boundary. And the first thing to do is, of course, to get the grain boundary, we need to have a raw model of the grain boundary, which there is some more complex algorithms. I'll put the relevant papers. Up on the YouTube video later when I post the video. But what we are going to do is actually we're going to start hand modeling because it's the easiest to understand, and for a lot of simpler cases like a grain boundary, you don't need any fancy algorithms. It doesn't take very long to just hand model it and then improve upon the mesh. Most of all, for single point analysis for interfacial axis values and for proxygrams, the mesh vertex distribution is not very important. It will only come in next time when we're doing local proxygrams and interfacial axis mapping. So yeah, there's not much reason for us to do that anyway. Okay, so the first thing we need is actually the hull of the data set. So we need to know what the outline of the data set is. In this case, it would be pretty easy because the entire data set is obviously convex. So there's no concavities in the data set, which means we can do a convex hull. However, for atom probe data, that's not, unless you cropped it out, and then as a boundary, as a hull, you can just use your cropping box. We'll go into how to use Blender to do cropping in your data set probably in some of the later lectures as well. But unless you've cropped your data when you actually know what the boundary is, an alpha hull is usually the way to go. And what an alpha hull is it's kind of like a convex hull, but just imagine it as all the volume that you can reach or you can't reach with if you're trying to fit a set of spheres with a certain radius to the data set. Because of course it's a point cloud. A point cloud doesn't have a defined boundary. There's always the analogy, if you would try to pour coffee through a point cloud, there is no place where it would settle. It would just go through. Just quite obvious, but anyway. So you need to have algorithms to extract the outside shape. And for that, we've got the sampled alpha hull algorithm. The reason why it's sampled is because atom probe datasets can get pretty large, and then an unsampled alpha hull might just stall your computer. And the other reason for it to be sampled is that if you have pointed as somewhat a little bit further out, you also tend to get very, very small triangles if you do that. And if you use 200,000 or a million points, then you're pretty much on the safe side. I've set a default to be 200,000 atoms, so you randomly take 200,000 atoms out of the entire data set, and that's what's used to create the hull. So I'll just go and create the hull equals sampled alpha hull, and what we need is the pos file, and we will use an alpha of 5 nanometers, usually because the concavities have pretty large radii. In the atom probe data, somewhere between 5 and 10 nanometers gives you a good mesh. But anyway, just have a look at it and see if it looks kind of like the way you want it to look. So this should only take a couple of seconds, and there we go. So this is the dataset hull. You can see when you rotate it around. We know that in this case it should actually be a cube, well, not a cube, but sort of like an elegant cube box shape. That's 40 nanometers by 40 nanometers by 80 nanometers, and it's not perfect, but it's pretty close. So 40 times 40 times 80 is 128,000. Sorry, I probably could have done that just in my head, but anyway, 128,000. And because we might not have sampled some exact corner atoms, we got 126,000 roughly. I think that's quite okay. But anyway, now we've got the dataset hull, and we might want to save the dataset hull, so just go patch to obj, add hull, and I'll just save it with the other example data, and it's test grain boundary underscore hull. And there we go. If you now go into Blender and go File, Import, Wavefront, OBJ, just make sure that it's Y forward and Z up. It's very important. And we go into Why does it not remember that I've been in that folder? Anyway, Dropbox, research, and then APT tutorials, example data, and there we go. And now we've got a HAL for our data set. As you can see, if we would have just by hand made a box, which in this case would be perfectly possible, it would have been a little bit nicer, but that's kind of okay. It will do the job. I'll just make it invisible for now, and the next thing we'll do is extract the grain boundary. So the first thing to do when you do that is actually you find a perspective wedge is looking down the grain boundary. And the easiest way of doing it is you take the solid that you want to use. You can actually join 2 or 3 solids together into one object as well. You would just go mark both. In this case, this is mark both, and you just go in the toolbox. And oh, come on, where's the join command? Anyway, why would it not join the? Oh, one's not visible. So you have to have everything visible if you want to do that. So if you now would go and join, Control J, you could join them. In this case, of course, we've only got one solid, so it doesn't make sense. But if you have, for example, a segregation of phosphorus and nickel and oxygen or whatever, and you want to use all 3 to do your grain boundary fitting, then you can just do that by joining them together. Anyway, and then just make a copy. Control Shift D. And don't move your mouse when you do that, because otherwise it's going to do this, right? I'm clicking press escape anyway. But try not to shift your data. That's very important. And that's why always having the same origin, as I mentioned last time, is also pretty important. And then next thing we go is into edit mode. And now I can see we can edit all the atomic positions. And the reason why I'm doing this is because I want to delete all the atoms I don't really care about. And the small screen is a little bit harder because I've downsampled the screen to run on the projector here. Anyway, one thing you need to make sure is that you're in wireframe mode. If you're not in wireframe mode, you can also just go into wireframe mode. The reason for that is that if you're in solid mode and you go and select something, you'll see that it only selects things it can see. Right? It's not what we want. We want to select everything that's sort of behind where we are. And if you go into wireframe mode, you can see everything that was behind it is actually selected. That's the way it should be. If we have a grain boundary, in this grain boundary we know it goes roughly up to here. But what I would usually do is move along the grain boundary with the circle select tool. Again, I know it's overkill for this example, but in reality that's how you would do it. Go, move along, and yep. Then go X and delete the vertices. And so I'm left with those here. The ones below here, we can actually just use a box select for. Get rid of, sorry. Yeah. Box select is B, by the way, and delete the vertices. Circle select is C, and box select is B. And same thing up here. And go X vertices. By the way, this is now for decom, and if we've got a little bit of time later, we'll do isosurface as well. MATLAB has isosurfaces built in, by the way, so doing isosurfaces in MATLAB is really easy. And now we're left with the items that we need. And now you can actually see that there's a pretty striking difference in terms of density between the two sides. Can you also see the small clusters that are on both sides in the grain boundary? Can everyone see them? That was actually a trick question. There is no clusters. This is what a random distribution looks like. So I've very often seen people point things like that out as very small clusters. It is actually perfectly random, and this is just random clustering. So that's why it's very important to always compare clustering to what would be expected as random. Um, so now there's two ways of doing it. So one way that I like to do it very often is just pick individual vertices and build a mesh up from them. That's mostly the case if I've got grain or face boundaries that are bent. So I need to make sure that there's there's edges running around the corners of where the bend is and things like that. Um, but if it's a fairly flat grain boundary like the one I showed before, what you would do is just go Shift Add Mesh Plane. Sorry, it's up somewhere in nowhere, in the middle of nowhere. So it adds the plane where the cursor is. So just put the cursor here and put the cursor here. So now you can see the cursor is uh, nicely in the middle. And then go show add mesh plane. And now we've got a plane that's 2 by 2 units. But of course we need it to be larger and we need it to be subdivided. And we need it to be subdivided unevenly. So there's two ways of doing it. The first one is just pressing scale, or it's three ways. Pressing scale, or you go into the scale handles. So you can also use the scale handles. But I don't use the handles. I started using them a little bit. And the other thing is, of course, if you've got a measure of how large the area is that you need to span, so you can go into the toolbox and go into grease pencil, and there's a ruler. You can go and have a look. Damn it. Use the ruler from here to here. Okay, we know it's 40. Of course, in this case, we've made it so we know it's 40. But in other cases, you would want to go and just measure that, and this is 80. And so what we can do is then go into the dimensions here, and we know that the x is okay. So if you look, there's one convention that people overlook sometimes, and that is if you look at any sort of axis systems, you will always see they're red, green, and blue. This is because it's made by computer graphics people. They use RGB and they use XYZ. So XYZ is always RGB. So X is red, Y is green, and Z is blue. If you look into Iverse, follows the same convention. If someone's not following the convention, they're just being a prick. Anyway, you should really follow the convention. Is XYZ is RGB. So you know red is X, and so we know in X the dimension should be 80. We know in Y the dimension should be 40. And there you go. And if we now go into into edit mode, we can see that there is only 4 vertices. Of course, we need a lot more vertices. Actually, for just doing grain boundary, we're just doing a proxygram or an interfacial axis value, that would actually be enough. So we could perfectly do that. There would be no error in this because it's perfectly flat. But of course, at a real grain boundary, you would want to subdivide it and would have a bit of a finer mesh because then we need to fit it as well. And in order to do that, you can press W, subdivide. But subdivide does that on a so if you want to use subdivide, essentially you need to have a square because otherwise it's going to be uneven in X and Y. So we can go Control R and we can use loop cut. And in this case, I'd say we do 5 nanometer pitch. So 80 divided by 5 is, damn it, 80 divided by 5 is 16. So we need 15 divisions because one's already there. 14, 15. There we go. Then just press escape so it doesn't slide around. And in the other direction, Control R, we need 40. It's 8, 7. 7. Oh yeah, it looks pretty square. So again, you can slide it afterwards. Don't slide it around. Just press escape, and now we've got square divisions on our grain boundary. So one thing I'm going to do is actually move all the vertices up a little bit, just so you can see the relaxing that's happening during the decom step in MATLAB, because otherwise, in this case, because it's synthetic, it would already be a perfect model for the grain boundary, but that's not very useful for demonstration purposes. And that's our raw model. And if you look at the other grain boundaries, it pretty much started out with a raw model like this. Of course, in Blender, there is always a large number of ways how you can actually model something. And maybe we'll go in some of the later tutorials, we'll go into details of what the different options are depending on what sort of data you have. Usually, all get you there, but sometimes it's more efficient to do it one way or another. That's just it. Okay, so File, Export Wavefront. For some reason, it doesn't remember. It doesn't remember why that I went to the Dropbox folder. Never happened before. Example data. So we've got the test grain boundary. Usually, what I do is I actually go into the data and copy whatever. So this is test grain boundary. Copy whatever the name is. Test grain boundary. In this case, of course, usually it would be some run number. It would be R04 something 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 underscore grain boundary, or could be from a lava tap or whatever. Anyway, and then raw. In this case, of course, we're not going to make many steps away from raw. Raw means it's just raw how I modeled it, and we need to make sure that we have wire forward. Selection only, very important, because otherwise it's going to copy out all that atom probe data as well, and it's going to be a huge file and it's going to be useless. Modifiers, if you've used some, but in raw modeling I would never use any modifiers. We're not going to include edges, normals, or UVs, or materials. We're going to triangulate the faces. In this case, I'll just let the exporter do it. Usually you would go and triangulate the faces in the model itself, but we'll just leave it as it is. And that's all fine. The only thing I want to say is next time when we're gonna do local proxygrams, we're gonna need polygroups, because we're gonna need to be able to say, okay, this is this part of the mesh, and we're gonna write it out to the OBJ file as well. And click export, and now we've got it. Now we've got it here as an OBJ. If you look into it, you've got the vertices again here and the faces here, and there should be one object. Starting here. Okay, so I'll go obj is read wavefront obj, example data, grain boundary raw, fv dot vertices, fv dot faces, and we've got our grain boundary in. So again, that's why it's always convenient to always use the same variable names and just shuffle data around a little bit, so you don't always need to type stuff in. Go hold on, and we'll just plot the grain boundary into the figure. Actually, we probably should plot the solid as well. How much solid do we have again? 200,000, so we need to downsample that. So sample, we're probably gonna make 10,000, can deal with that pretty okay. And scale data source same. Oh, why? Why is this so? Ah, we need all 4 columns. I just copied the first one. There we go. Samples, scatterplot. Now it should all be here. So now we've got the dataset hull. We've got the solids in there. And what we're gonna do is I'm just gonna delete the hull. Don't need it for now. But yeah. And P equals patch V. I'll just plot. So this is our first approximation, right? So this is how we pull it out of Blender, and all we need to do now is actually fit it to the grain boundary. So in order to get so that what the decom algorithm does, that is a fitting algorithm in here, is essentially it goes and draws a sphere around each of the vertices and calculates the center of mass for all the atoms we're using for the fitting, and then moves the vertex along its vertex normals. So it doesn't move it sideways, it just moves it along the vertex normals, because otherwise the vertices would start bunching up. But you can look into the papers to understand exactly what's happening. It's not very complicated. It's just being essentially pulled to where the most atoms are along the vertex normals, and within a certain radius. And that radius is very important. Therefore, actually, if you've got reasonable segregation, it doesn't change much with the radius. But if the radius is too large, what happens is that it can get pulled sideways, especially on the boundaries. So the radius we want it to be is about the half of the thick width of the feature that we get it pulled to, or that the diameter of the sphere is pretty much the width of the thing we're trying to look at. And if we're looking at the if we're using a ruler again and have a look, then we'll know it's about 5-ish nanometers thick. So the radius we could use is about 3 nanometers, and it's 5-6 nanometers. So just remember where it was first, and then we go fv2 equals decom step. We'll just do one step, and we'll actually have a look at the energy as well. Is decom step okay? It's pretty much, to be honest, most of the grain boundaries I see have about a width of 5 nanometers, so usually you pretty much end up with very similar values. This is actually from a real analysis, it is not from synthetic data. Same story there. Okay, we're starting from the first one, and that's it. And just to explain what E is, so E is the energy, and you can use that for convergence, to assess the convergence. So if you go decom instead of decom step, so decom step is just one iterative step of fitting the grain boundary. What it does is it does the fitting multiple times until this energy, relaxation energy, goes below a certain percentage of the original value, usually below 5%. And this is something that's very regularly used in mesh adaptation algorithms. And what the energy is just the sum of the square of all the displacements that happened, right? So just imagine it's the energy that, if this was a spring, this is the energy, this is a measure of the energy that a spring would be released, like jumping back into its original position. Of course, the better you modeled your original grain boundary, the less relevant, the less useful this will be, because your relaxation energy will be very low from the beginning on. So you can just judge by looking at it whether that's a lot or not a lot. Anyway, but that's the convergence energy, just as a heads up. And now this is our original grain boundary. And if we have, after the first step, P equals patch. Oh, come on, it must be one with a 2. Yep. And we'll make it a different color as well. And now I can see it did not actually move very much, so maybe it was not really enough, because we've actually moved it off center quite a lot, which is probably for an example good, but anyway. So we'll make that, instead of 3 nanometers, probably 6 nanometers, and have a look. Okay, I'll just delete the other patch so it's not in our way. We'll just do it with a larger relaxation. And because we've moved quite a fair bit off center, it will actually need more than one step. So just remember, our first step energy value was 110. So if you look here, it's 110. And now for our next step, it's 74. So it still moved a fair bit. But we're getting closer. Of course, it gets pulled stronger where there's more excess. But yeah, we're definitely moving closer. But again, we've moved it off the actual grain boundary fairly seriously. In a real case, you probably wouldn't do that. Anyway, another step. And also, I've made it with relatively little excess compared to real grain boundary. So we've made it a little bit harder than it would usually be, but I guess for instructional purposes, that's quite okay. I have another plot, but now we're getting pretty close, and you can see that the convergence, the energy is going lower, and actually by quite a lot. So we're going to about 48 down from 110, 31, 21, and now we're gradually getting closer. The problem is just at the corners where you can imagine that the grain boundary actually, the sphere that does the fitting actually goes outside the volume, which is nothing we can do anything about. There we're getting into a little bit of trouble. So the original value was 110, so that's 11, 5. So 5 would be sort of the convergence criterion in this case, which we might not actually reach, simply for the reason that that the sides will already start folding up and see more displacement before we actually reach the absolute minimum. Anyway, 16, 13, 12, yeah. So we're sort of converged to that, and if we go past, that's probably because we start curling up a little bit, yeah, on the corners. But really, we are pretty much on the boundary, and you will see that when we look into that in Blender. If that happens to some of the vertices at the boundary, you can just manually fix that. So we'll just go patch to obj, and this time for v2. Example data, grain boundary, decom 6 nanometers, and save. And now file, import wavefront. There we go. We just need to make sure it's Y-forward. Yeah, we've already imported something, and there we go. So it's pretty much sitting on the grain boundary, apart from a couple of vertices on the sides that are a little bit off. Reason again is that it starts curling up on the sides because part of the decom sphere actually goes outside the dataset. Anyway, can easily fix that. So nope, wasn't one of them. That one. All right, that's looking pretty okay. That one probably needs a little. Yep. A bit of manual adjustment as well. Anyway, so you can see it's not as perfect as if we would just have put a plane in, which we know would be correct because it that's the way we've synthesized the data. But it's a fairly good approximation. Okay, one algorithm we would still need in. Oh, okay. So I've unfortunately shifted that one also in the other direction. I'll just move that back. Is stretch to boundary. So usually your um, your grain boundary would not perfectly conform to your dataset boundary. In this case, of course, it pretty much does, but this is actually just one algorithm. So you just go fv3, let's call it fv3 equals stretch to boundary, and this just does it for you. It tangentially stretches or compresses. So for that matter, if your vertex is outside the boundary, it pushes it onto the boundary or inside, so that it perfectly lies on the boundary. It's tangentially extended. Okay. So if you have something, that's sort of curling up on the side, it would also move it a little bit up on the side. And if you have if you have some sort of grain boundary or interface that's meeting the hull at a very acute angle, of course, this gives you also some source of error. But again, check it in Blender, and if you need to, then just manually adjust the analysis mesh. So I'll just patch to obj fv3. So we'll just export that one now. And just override it. We're just going to need that version anyway. Yes, replace please. And then when you go into Blender, file, import wavefront, everything's set up this time. Then you can see that, oh, well, there was one tangent that was not as. So you can see this one's the original one, and the other one's just a little bit stretched. That one, there must have been a. Let's have a look at the mesh here. Yeah, so you can see it's not quite meeting, and probably also has some triangles with weird angles. Yep, that's what I said. We can easily fix that. So need that one. Can easily fix that. Just move it back up to where it belongs. But apart from that, if we now go back to solid visibility mode, it would probably be some mesh adjustment. In this case, for the synthetic data, it would have actually been better the way we had it originally. But anyway, stretch to boundary is something that you would usually need. If you look at it here, you can see a very uniform line going around. Of course, with the limitations that the hull is not perfect either. By the way, we can produce much better hulls if we co-reconstruct them with the atom probe data. So if we produce the hull for the dataset while we're reconstructing the dataset, the paper for that isn't out yet, and you can only do that if you do your own reconstruction. But that of course gives you a much nicer hull. Let's just have a look at one. This would be one. So this is this is a reasonable dataset hull that's been co-reconstructed. So nice squares everywhere and very even distribution of vertices. Anyway, if you just have your data out of other software that's reconstructed it, you have to live with the alpha hull pretty much. Anyway, so this is our grain boundary here, our model, and you could use that for visualization already. But of course, the next thing we want to do is some analysis, and maybe I should also check if someone in YouTube has had some comments on what we're doing so far. Nope. So next step is calculating a proximity histogram. And for that, we're actually going to look into the code of a proximity histogram and of the interfacial axis value, simply because it's that simple. People always think it's like, oh, it must be so complicated because it does 3D stuff. It's actually not complicated at all, and interfacial axis value calculation isn't either. So if we go here into quick proxygram, just open up the window. How can I undock that? Undock. So this is the entire code, and this part of the code is actually just plotting the proximity histogram, and this is all the code we need to calculate it. So this is the simplest form. So the simplest form means you give it a pos file, you give it a pos variable containing all the solid you want to create a proxygram for, and a parent pos file. So this is the pos file the sub pos file comes from, ideally with all the noise removed, because we don't want to calculate concentrations based on noise. And the noise usually is about 3 to 5% of your data set, which sounds way worse than what we advertise atom probing for. But the reason for that is that noise occurs at any master charge level, no matter whether you have a peak there or not. So if you just look at the noise that's there where there are peaks, it will be much lower. So it will be in the sub% range, probably maybe 0.1% or something like that. But because your mass spectrum goes from 0 to say 500, you still have the same noise from 100 to 500 and from 0 to 100, even though you might not have any peaks there. And of course, if you've got a reflectron-based machine, you also have a little bit less noise as well, because it's a little bit narrower. The peaks are a little bit narrow. Oh, quite a fair bit narrower actually. Anyway, so the proximity histogram works by with these two pos files in the easiest version. In the more complex versions, actually you can throw in multiple ones and it gives you the entire plot. But I think this is the easiest one, and usually I just use that one, because if you calculate it for multiple species, you can just copy paste one proxygram into another. Like just in a MATLAB figure, you just mark whatever plot you want to take and just copy it into the other one and combine them this way, and you don't get anything into a twist. The other thing you need, of course, is the interface. By the way, this is one without error bars. The error bars is essentially determined by the statistics in the bin, so 1 over square root of n. Maybe I'll just throw in some error bars for next time, but calculating the error bars is pretty trivial. Statistical error bars, by the way, I always want to emphasize that if you publish something and you see error bars on the proximity histogram, that's not the real error, that's the statistical error. It's very different things. Usually we don't know what a real error is. And of course, we need to know what the bin size is. So we need to just say what the bin size is. For a grain boundary, usually the statistics are pretty good. So usually you can go to, I don't know, half a nanometer or a quarter of a nanometer, something like that, and still get pretty reasonable values. Below a quarter of a nanometer, it doesn't really make all too much sense, really, because not our models doesn't matter whether it's an isosurface or whether it's a decom model. They're usually not precise enough to really see any detail smaller than a quarter of a nanometer. Definitely not a quarter of a nanometer. Usually not finer than half a nanometer. So just to give you an example, and of course, if if your data is crazy noisy, then you know that you need a larger bin size anyway. So what we then do is for the interface, we calculate the normals of the interface. So for every vertex, we calculate what the surface normal is. So essentially what direction is perpendicular to the interface. And then that's actually the next calculation is repeated once for the parent POS file and once for the solute. The reason we start for the parent POS file is because we want to know where the cutoff is, like how far do we need to calculate the proximity histogram. Do we need to go to plus 100 nanometers and minus 100 nanometers, or just need to go to plus 10 and minus 10 or something like that. And that's why we start with that. And what we do is for each vertex, for each atom, we calculate which vertex is the closest. What that is essentially a Voronoi decomposition of the data set, and you'll get sort of a cylinder shape. I think I went through that last time. Otherwise, just look in the papers, in the comments, yeah, you're just creating a cylinder shaped volume around the grain boundary, around the interface, and we're measuring our concentration profile along that cylinder. That's essentially what it is. And this just shows us which vertex is closest, and then we calculate the distance vector for this atom to that vertex, which is just the position of the vertex minus the position of the atom. It's just simple vector math. And the distance is then a dot product of the vertex normal, the normalized vertex normals. You need to make sure that the vertex normal actually is normalized. In this program, it is actually normalized, but if you wouldn't know, you need to actually make sure it's normalized, so the vertex normal has a length of 1. Otherwise, of course, the distance length would be off. And you do an in product, which is just this. It actually MATLAB has a dot product, but dot product is so simple that just writing it out is a little bit easier, and I haven't gotten into how to do that for entire matrices. Anyway, and that's all there is. The rest is just a histogram. So a proxygram is just a histogram of those distances divided by a histogram of those distances for the solute. And in order to calculate that histogram, we need to know where the bin centers are for that histogram, and that's what's happening here. And you just create a linear space back and forth. So I made it 1,000 bins back and forth. So if you ever have a data set that's larger than 1,000 bins, you would need to change that. You could actually change it to 10,000. It wouldn't actually make a difference really. But let me think about it. So 1,000 bins for a quarter nanometer would be 250 nanometers. Yeah, you could actually run out of distance in this case. Should probably make it 10,000. Sorry. Anyway, if that ever were to happen, that's what the error is. Anyway, oh no, this is just for one direction. So it will be 500 nanometers in one direction if you have a quarter, and 500 in the other. But still, like if people have nanowire data sets that are a couple microns long, so why, they could get into trouble with this. And it just creates that bin vector and just throws out all bins that extend beyond the data set, creates a histogram, and then this entire process is repeated for the solute, and then the proxygram is just histogram of the solute divided by histogram of the entire POS file, and then plot it out. And that's all that a proxygram is. So we'll just run that. So proxygram actually just plots it out. So it's called quick proxygram because there is some not so quick ones with all kinds of options on it. We've got our solute, we've got our POS file, we've got our interface, which is FV3 in this case. That's the optimized one. Let's use FV2 because it didn't have the weird boundary thing. Anyway, whatever your best interface approximation is, and then just let it run. Ta-da! Of course, towards the you might have a bin towards the end that has 2 atoms in it, and then suddenly your concentration is way off. But yeah, that's the proxygram for the grain boundary. Looks pretty okay. It looks pretty much what it should be like. You can compare it to the reference distributions in the Synthesize data in the Synthesize thing. But yeah, proxygram, easy. The only thing in formatting you'd probably do is go into the axis, and because that the ones at the corners are not really at the end are not really representative of anything, so you'd probably go from -20 to 20. And actually it goes to -25 because there is some, so you can actually look at the surface normals in Blender. Did we actually triangulate? We triangulated, yeah. So if you go into edit mode, and just scroll down here, you will see normals. And we want vertex normals, so you can have vertex normals, vertex per face normals as lines. Okay, I have no idea what that means, but there's vertex and face normals. Anyway, they can see the I have to find out what that one is. Anyway, you can have face normals, obviously, and you can have vertex normals. And you can see some of the vertex normals are actually not pointing perfectly outwards, so you might have a little bit longer distance here where you still find data. Anyway, it calculates along those normals. So yeah, that's all there is to a proxygram actually. The only thing is I'll just calculate another one just to show you how to copy one into another. Just go and delete. Can just go and mark that one and delete it. Then you can go and select that one. So you go to the select tool, select it. Usually, you would go and change its color to something else. Then you can go command copy. Then you need to go into the axis here. So not the figure, the axis. So now if you see that corner selected, that's the axis. And then Control V, and you can copy it in. So usually I start with one proxygram of one species, formatted it the way I want it to be, and then do proxygrams for the other species I care about, and then just copy it over. And add a legend, and that is called solute. And slowly you'd build up. You'll build up along a list here, and that's what you would put into a publication. That's why I've already given it a white background, and you can format it into publication format and export it as an EPS, and it will show up as a proper vector graphic rather than some shitty bitmap or whatever pixel graphic. Okay, so now we've got a proxygram for that interface, and the last 20 minutes we're going to spend doing calculating an interfacial axis for the same grain boundary. I don't know if that's actually going to take us 20 minutes because we've got everything laid out already, and in order to create an interfacial axis value, maybe I should explain the reason why you want an interfacial axis value. So if you do a grain boundary, or especially if you analyze grain boundaries and interfaces, the concentration at the interface is not really representative. If you just imagine you've got a certain amount of solid sitting at a grain boundary, the concentration you measure will be different depending on what orientation that grain boundary had in your atom probe sample. So if you take the same grain boundary and lift it out in different directions, you will get different concentration values. Two reasons. First is local magnification. Second one is preferential retention. But the one thing that doesn't change is actually the overall amount of solid in there, and that's what the interfacial axis is. It's essentially counting, okay, how many atoms per square nanometer do I have, or per square unit do I have? And that's usually done on a cumulative curve. So you could actually do that here as well. I've sometimes done it on a concentration curve as well. For some cases, it's advantageous, but usually we do that in a cumulative curve. And what that is, I'll show you in a second. So we'll go quick axis value for solid, pos, and FV2. And if you type that in, it will actually come up with a nice graphical user interface for you. That way you can do your interfacial axis values. Let's just wait for a second, because in this case it needs to do some sorting. But even for a 12 million atom data set, it would usually not take longer than 20-30 seconds. There we go. And what you get is a graph, a cumulative graph, which is cumulative number of atoms. So it's cumulative number of atoms sorted by distance to the interface. So you're starting with the one that's the furthest away from the interface on the negative side, which brings me back to the importance of surface normals or vertex normals. So vertex normals can actually be flipped. So if you go and say manually create an atom probe dataset, you might end up with a situation like the one I've artificially created here, where some of the faces point to the wrong side, just because that's the way you've created it. And if that happens, you just mark all of your vertices and you go recalculate. Okay, so now it's recalculated them. Now it's flipped the direction. So that's the other aspect of it. If you have different concentrations on both sides, it's also important to know which side's which. And the plus side is the ones that the blue lines point to, and the minus side is the one that points away. So this is the way we had it before. And again, if you create your own analysis object, just before you export, make sure that that all of these point into the same direction. If we switch the solid off, you might be able to actually see that. Now you can't see anything, but if I go and flip some again, then you will be able to see that the shading gets weird where the UVs are, where the normals are flipped. So if you make an object, especially if you go, why does it go away from shading and UVs? Smooth shading, you will see shading artifacts. And if you see anything like this happening on your mesh, then you know that it's probably the UVs and the normals that are flipped. And I need to go into the object and just make sure that they all point into the same direction. Anyway, for us, we know that was the case, and so you end up with a curve of all the atoms ordered by distance along those blue lines, along the surface normals, versus the cumulative number of atoms of whatever species you're looking at. So in this case, it's solid called SOL. And if you have a constant concentration, this produces a constant slope, and that's what we're getting here. And here on the other side as well. And if you have a higher concentration, it's a higher slope, and if you've got a changing concentration, it's a curve. And that actually makes it fairly easy to pull out the interfacial axis, because at the 0 point, so it just searches for the atom that's the closest to the interface. At the 0 point, we're calculating the difference between the number of atoms that would be expected from this curve and the number of atoms from this curve. Yeah, and that's pretty much it. It's very simple. And the reason why this is a graphical user interface that allows for interaction is that you might have crazy changes in concentration here on the other side. Now I can't just show you the analysis I've done this morning, unfortunately. So you can press change limits and click at the bar that's closest to, click close to the bar that you want to move. By the way, you can only see 2 or 3 bars, but that's because the 4th one is right at the boundary, so you can't see it. But we could, you could move this one to here, and now I've got an approximation from here to here and from here to here. Now, of course, nothing changed because this is a really absolutely constant concentration, but I could change that one from here to here, and it would change slightly. But I think one thing that becomes pretty obvious is that I've moved it to a place where it's obviously wrong, and the interfacial axis has changed from 8.8 from 9.8. So you can see this is a very robust method of determining interfacial axis. Of course, if you've got things like non-equilibrium segregation, you need to justify how you did it, because there might be a lower concentration around the grain boundary, and then there's 2 ways of doing it. You can have, you can determine interfacial axis relative to the lowest concentration that's next to the boundary, which is sort of the short-term interfacial, the short distance interfacial axis. If you were an atom, you're trying to diffuse around. Essentially, your chemical partitioning that you see is, okay, I'm sitting here and there's a lot of the same atoms, but if I just look there, there's almost none. You wouldn't see anything beyond that, right? But for thermodynamic reasons, you might be looking into what is the global interfacial axis. So what is the number of atoms there compared to the bulk that's behind it. Anyway, that's not a question of the analysis method. It's really a question of the science behind it. But yeah, with that, you can actually you can change it around. And once you're happy with that, and you want to put that into a paper, probably the figure itself is not that interesting. Everyone knows what the cumulative curves look like. But sometimes you might need to put it into the supplementaries, or you just keep it for later reference, and you just click figure save, and it saves it as a MATLAB figure. So I would go into the example data, and I would go decom 6 nanometers solute interfacial axis, and go save, and it saves it out to a MATLAB figure. Once it's done saving, it will actually get rid of the figure, so it doesn't clog everything here. Anyway, and that's actually how to do interfacial axis measurements. It's fairly simple, right? So as you can see, with a little bit of experience, you'll probably be able to do that like me, to create an analysis model and calculate proximity histograms and calculate interfacial axis values probably for a grain boundary within an hour. It's really not very hard. The programs that I've put out are the simplest versions. Of course, there's more sophisticated versions that do all sorts of other things as well. But all these other things you can do by yourself in the MATLAB workspace, which is usually less confusing than just getting your head around my programs. So I'll just stick with the simpler versions. I don't think you will have much of an issue trying to do that. All right, so I think that's pretty much it for today. So we went through modeling of a grain boundary. Sorry, we didn't get to how to create an isosurface. That's something we're going to do next time. So next time we're going to do an isosurface. Along with the isosurface, probably volumetric. So how to, an isosurface is just a visualization of a voxelization. So we're going to go into the voxelization, how to calculate the isosurface, and how to do the analysis based on an isosurface. All right, so that's it for today. Thanks for everyone that was joining in, and have fun with the videos um, and with the algorithms behind them. And see you next time.